Alright, this is video 1 for the simple harmonic motion unit. So for this unit, we're going to use big ideas 3 and 5. So for number 3, the interaction of an object with other objects can be described by forces. And number 5, changes that occur as a result of interactions are constrained by conservation laws. Learning goals for this unit. I want you to be able to determine the motion of a simple harmonic oscillator and determine what that motion depends on. I want you to be able to construct qualitative and or quantitative explanations of oscillatory behavior. And I want you to be able to use conservation of energy to explain the motion of a simple harmonic oscillator. So let's get into simple harmonic motion. This can be described as the motion of an object moving back and forth, usually from some rest position. There are two types of oscillators that you will be responsible for the AP exam. The mass spring system and the pendulum system. Those are the only two oscillators you have to worry about. So as an example here, imagine we have a box and we have it attached to a spring on a frictionless surface, and we pull this box and then release it. This box will then oscillate back and forth across some initial position. And since we're not including friction, this would oscillate, theoretically forever. So that is simple harmonic motion, something moving back and forth across some equilibrium position, just oscillating back and forth. So what we need first off is a restoring force. Restoring forces result in oscillatory motion. So for the mass spring system, the elastic force of the spring is trying to restore the system to its initial state, to that x0, that initial position. So when we have a linear restoring force exerted on an object displaced from equilibrium, the object will undergo simple harmonic motion. All right, so for the spring that exerts this linear restoring force, the period of the mass spring oscillator increases with mass and decreases with stiffness. So period is a unit of time. And for the period of an oscillator, it's from its release point back to the release point, that amount of time. So for the mass spring system, the period will increase if we put a larger mass on there because it has a greater inertial mass. It's harder to accelerate, so it will take longer for that large mass to move back to its initial starting point. Or if we increase the spring constant, the elastic force becomes greater, which means that the force is becoming greater, so it will accelerate that mass easier, and that will cause it to move faster, so it would have a smaller amount of time as well, or smaller period. So let's take a look at this mass spring system in a little more depth. So here we have the starting point, so we can call that like our x. Here we have our equilibrium point, or x0, and right here I can call this negative x if I want to, where it's going back to the other one. Now notice, because of conservation laws, if I displace this initially by positive 3 centimeters, it will travel to negative 3 centimeters on the other side of the equilibrium point. It's not going to go any further because, well, it doesn't have enough energy. All the energy has been exhausted. So then, when we take a look at this, we can start looking at the forces acting on this block. So the net force acting on this block is that elastic force. And notice that when I displace this in a positive direction, I have a negative force. There's only one force acting on this block in the x direction. So we can say it's not in equilibrium, so it's going to equal m times a. So for elastic forces, the model for elastic forces is the spring constant times your displacement. So for us, it's being displaced by some unit x. Got our negative sign there, equals mass times acceleration. Now remember, acceleration is the second derivative of position. So I can go ahead and replace acceleration with that second position there, or that second derivative. So then, looking at this, I can rearrange this formula to look like this. And this is very, very important. This right here is called a second order differential equation. Another way I can rewrite this is I can rewrite this like that. This right here is the formula for simple harmonic motion, or the equation for simple harmonic motion. It is well beyond the scope of this course to try to find out the solution of the second order differential equation. But there are some things we can pull from this nonetheless. When you get to college and you take differential equations and you learn how to solve second order differential equations, basically what we do is we guess a solution to this equation and then check to see if it works. This does have a solution, and the solution to the second order differential is this equation right here. Now, A is really the maximum amplitude. So we can think of A as being, our x. A is the farthest that you pull that mass away from its equilibrium point. So A, and usually A stands for amplitude. So it's like the greatest position away. Sine is obviously the sine function. Now for this omega, well, if we take a look at the simple harmonic equation, we see that we have this omega squared. And that omega squared took the place of k over m. So omega will equal the square root of spring constant divided by mass. Omega has a special name. It is called the angular frequency. So angular frequency is defined as being 2 pi times the frequency, where frequency is measured in hertz. Frequency is how often something happens per second. So how many times does this oscillate back and forth per second will be the frequency. Frequency then is defined as 1 divided by the period. Again, how many times does an event happen per second? That's what the frequency is. So I can take a look at my angular frequency then as being omega equals 2 pi divided by the period. And that's kind of important right there. We want to make sure that we want to represent this in terms of period. So the period then is how long it takes it to go from its starting point all the way over and then all the way back. That's what the period measures, how long that event takes. So now I have two equations for angular frequency, the omega, so I can put them together. And what this does is it gives me a formula to calculate the period. Now this is important, and that's something that's on your AP formula sheet. So notice then, so we go back up to that definition up there, the period of the mass spring oscillator increases with mass. So notice as mass increases, period increases from our period equation down here. and it decreases with spring stiffness. Now spring stiffness then is the spring constant, so notice that as K becomes bigger, T becomes smaller in that period equation. But that is the mass spring oscillator. Now as this thing is oscillating back and forth, notice that the minima and maxima and zeros of position, velocity, acceleration, we can find all these. So at the very ends is where this object comes to rest. So that positive x and that negative x. That's where this thing comes to rest. However, that's where it has the greatest acceleration, because that's where the greatest net force is. At x naught, near the middle point, that's where the acceleration equals 0, because the net force is 0. The spring is in its relaxed state. However, that's when it's moving at its maximum velocity. So we have this relationship here where on the ends we have the greatest net force, giving us the greatest acceleration, but 0 velocity. Remember, just because the velocity is 0 does not mean that the acceleration is 0. And at the middle, we have the acceleration equals 0, the net force equals 0, but the velocity is at its greatest point. So what else that kind of also means is that on the ends we have potential energy, for this case elastic potential energy, and at the middle point we have kinetic energy. So if we take a look at conservation of energy, we can see that the elastic potential energy is becoming kinetic energy, which then becomes elastic potential energy, which then becomes kinetic energy, back to elastic potential, and just oscillates back and forth. So some things I expect you to be able to do. You should be able to calculate forces. You should be able to calculate accelerations for any displacement on the spring. And that shouldn't be too hard to do. All right, that concludes video 1.